We'll get started. So we were discussing about reachability, controllability, and what are the conditions under which a state is reachable or controllable in linear systems. So we are going to do the following. I'm going to recall some of the stuff we talked about in the previous class. So I'm looking at this system. For now, we are looking at reachability. So I want x0 to be 0. I want xt to be some final state xf. So I have a robot. Right now, the robot is at rest. I want to make the robot go from this position to this position and maybe pull this, right? So the xf is like being able to reach this particular position in a finite time period, capital T. Capital T is greater than 0. And in the previous lecture, I talked about this controllability matrix. So this is B, AB, A raised to n minus 1B. This is in n cross Mn. M is the dimension of U, n is the dimension of X. This is the controllability matrix. And then we talked about the controllability Gramian, reachability Gramian. WR, this is 0 to T. This is the matrix in Rn cross n. Okay, and then we talked about Cayley-Hamilton theorem. Which is P lambda equals to determinant lambda I minus A. And then the theorem says that P of A equals to 0. This is n cross n. So wherever I have lambda in this polynomial, I'm going to substitute lambda with A, 1 with identity matrix, and the polynomial of A is going to be equal to 0. So this is the characteristic polynomial. So this is all the stuff that we talked about in the previous class. It should be there in your notes from the last lecture. Towards the end of the last lecture, we were talking about these matrices. And one of the upshot of Cayley-Hamilton theorem is the following. Remember that P of A, what is P of A? So P of lambda is lambda raised to n plus beta n minus 1 lambda raised to n minus 1 plus beta 0. So P of A equals to A raised to n So we get this implication. Consequently, exponential of AT, which is summation k equals 0 to infinity a raised to k t raised to k over k factorial, can be written as summation alpha kt a raised to k equals 0 to n minus 1. So that's the implication that I want to write here. Exponential of AT equals to summation k equals 0 to n minus 1 alpha kt a raised to k. Okay, so these are all the results and implications that I wanted to remind you. And I wanted to pause here for questions. So this is a new result. This is a result that you haven't seen before, but it follows directly from Cayley-Hamilton theorem. So wherever you see a raised to n, you can substitute this expression, which is in terms of a raised to n minus 1, a raised to n minus 2, all the way to a raised to 0, which is identity matrix. And so I can do that substitution here, and I get alpha k as a function of t, and then a raised to k, which is where k goes from 0 to n minus 1. So this was contain all the t raised to k over k factorial terms and some beta 0 to beta n minus 1 terms. That is all embedded within this alpha kt term. Any questions so far? I think it follows straight away from the Cayley-Hamilton theorem. I haven't proved Cayley-Hamilton theorem, but this is proved in the appendix of the book. So I'm sure if you're interested, you can go to the appendix of the book and you can find the proof for that particular theorem. Any questions so far? Okay, if there are no questions, then so we have a disturbance in this room. So the air conditioning system is trying to cool the room, this is trying to heat up the room, and so that's what we are trying to do. How do you control the system under disturbance? Okay, so now I want to talk about some important results based on all of this stuff. So these are the preliminaries. And I think the most important result that we will study today is as follows. Oh, what's the goal today? So the goal here is find ut such that xt equals to xf when x0 equals to 0. We are going to do something more complicated towards the later half of the course of the class, but I think in the beginning that's my ultimate goal. But I want to prove the theorem from a small result, which is lemma 5. Is it 5.10? Yeah, 5.10. Which says that range of the controllability matrix C is the same as range of reachability matrix 0t for all t greater than 0. This is the most important result. Okay, how do we go about proving this result? What's the way to prove this result? So range of C, the range of this controllability matrix. So what's the range of controllability matrix? So if you multiply it by a vector, what are the, so you have mn dimensional vector that you can multiply it to. You will get a space in Rn, a subspace of Rn. So that's range of C. Range of WR0t, which is this horrible looking integral, which has all kinds of stuff. It has exponential, matrix exponential, it has B transpose, it has another matrix exponential, then I'm integrating it with respect to d tau. So this is a horrible expression. But I still get a matrix. At the end of the day, after doing all this integral, I get a matrix in n cross n. And the range of this n cross n matrix, sorry, a range of this n cross n matrix is the same as the range of this n cross mn matrix. Is that obvious? Is this an obvious result? Do you think that we can prove it easily? Or in some sense, I have two matrices. I want to show that the range is the same. What is the way to show that the range is the same? How do you show that two sets are the same, are equal? So typically speaking, the way you prove this result is that you prove that one set is a subset of the other, and then the other subset is a subset of the set. So you basically have to prove the implication both ways, that this is a subset of this and this is a subset of this. Okay, but we are not going to prove that because this is a subspace. There is an easier way to prove this result, which is I will prove that range of WR0T is a subset of the range of controllability matrix, and then the step 2 would be the kernel of WR0T is a subset of kernel of C. And that's going to help us establish this result. Let's establish step 1 first, and then we will move on to step 2. So I can write okay. So I know this result. So what is range of WR0T? So I have V in Rn. Well, okay. Let's look at WR0T. This is given by you know what? I have this exponential of AT is given by this expression, so I'm going to substitute it here. This exponential of AT minus tau and A transpose T minus tau. I want to substitute things from here. What do I get? I get summation of, this is integral 0 to capital T, summation of alpha k capital T minus tau a raised to k goes from 0 to n minus 1 B transpose, and I have summation T minus tau a raised to transpose raised to k 0 to n minus 1 d tau. Okay, so I have x is in, so let's say x is in this. This implies that there exists a v such that x equals to v is in Rn. So I am going to write x as I'm going to write it in a complicated manner. I'm going to do summation k equals 0 to n minus 1 a raised to k b integral 0 to capital T alpha k t minus tau b transpose exponential a transpose t minus tau d tau times v. This one is R n cross m. This one is R m cross n. R n cross 1. Does this make sense? Any questions so far? Okay. So I'm going to, even though I can do this, I'm going to replace it with exponential of A transpose T minus tau. I'm not making any change there. And whatever is the first term, I'm going to pull it out of the integral. So A raised to KB is sort of a constant. So I'm going to pull it out of the integral. Then I have the integral. I have collected all the terms with integral here. And then I'm going to multiply it by the vector V. So what is M? This is a matrix in M cross N. I'm going to multiply it by a matrix in N cross 1. Right? So I'm going to get a matrix in M cross 1. And I'm doing this X is summation. So this implies that X is summation of A raised to KB times V tilde I. Or I should say just V tilde for now. V tilde K, sorry. K goes from 0 to n minus 1, and this implies X is in range of C. Because I'm able to construct m cross 1 vectors such that X can be written as summation of a raised to kb times v tilde k. That implies that X is in range C. So v tilde k is v multiplied by this integral with alpha k here. Okay, and that implies that range of WR is a subset of range of C. So any point in the range in WR, I can construct a vector v tilde k such that X can be written as combination of the columns of controllability matrix, and therefore X is in range of C. Okay. So this proves step 1. Questions? Is it obvious now? At least step 1 is obvious, that I have this horrible looking integral, but the range of this horrible looking integral is the same as the range of the, I mean not same, but right now this is a subset of the range of C matrix. Now I need to prove that kernel of WR is a subset of kernel of C, and that would imply that the two ranges are the same. So now this step 2 is what we need to prove. Any questions on step 1? I think it's fairly straightforward. Let's go back to step 2. Okay, what does it mean for V to be in kernel of WR0T? This implies that V transpose, I mean, technically this implies that WR0TV equals to 0. This implies V transpose V transpose WR0TV equals to integral Okay, the reason we are doing the proof is because we want to understand how to manipulate these matrices and how to understand how these matrices work. Okay. Anything unusual that you see here? Anything unusual you see in this integral? So V is in kernel. So V, I multiply the matrix by V, I get 0. I can pre-multiply it by V transpose. It doesn't matter. I'm multiplying it by a 0 matrix. I'll still get 0. I do the same thing here. Do you find something unusual in this matrix, in this integral? Or do you see a pattern in this integral? No, no pattern. So this has to be equal to 0. Well, if you look at this matrix, and if you look at this matrix, they're actually transpose of each other, right? So they are transpose of each other. And I'm doing this integral of this matrix transpose d tau, and that's equal to 0. What does that mean? It means that each of this term is equal to 0, right? So this implies that V transpose, oh, I think this should be kernel of C transpose. Let me check. Yeah, I think it should be kernel of C transpose. Yeah, C transpose, sorry. Okay, this is kernel of C transpose, not kernel of C. Please make that change. The first one is still fine. Second one, this should be C transpose. So I do V transpose exponential of AT minus tau B equals to 0 for all 0 less than tau less than equal to capital T. Okay, so V is non-zero, this is non-zero, this is non-zero, and turns out that this whole integral is supposed to add up to 0. You're taking a matrix transpose matrix, so it's kind of a norm, and the norm, integral of norm is equal to 0. That must imply that each vector within this norm must be equal to 0. Otherwise, if you have a non-zero term here and you are integrating it, you should get a non-zero term here. Okay. So I have this. Now I'm going to again apply this particular result. So I get V transpose summation of alpha k t minus tau a raised to kb equals to 0. K goes from 0 to n minus 1. This implies that V is in kernel of C transpose. I'm kind of very unhappy here because I'm using T, capital T, as both transpose as well as terminal time, but I hope you understand from the context which one is transpose and which one is terminal time. Okay, so kernel, so basically V I have this, so this is what is defining the C matrix, capital C matrix, the controllability matrix. And so I have some, this one is just a constant, a bunch of constant for every tau, no matter what tau you pick. This is just going to be a bunch of constant. And so V transpose A raised to KB is going to get you to 0, as a result of which V is in kernel of C transpose. So that's what. So that allows us to conclude that range of C, range of the controllability matrix, is the same as the range of WR reachability Gramian. Okay, now let's turn our, so if there is no further questions, I want to turn our attention to the final goal that we have set out for today's class, which is I want to find a set of control actions so that my terminal state is XF. My goal is I have a robot. I want the robot to move and hold this particular thing. And so that's the XF. So XF is basically this position. And I want to figure out if there is a control action, set of a sequence, I mean, not a sequence, but a time, a function of time of action so that X capital T, which is at the terminal time, it is at XF. That's my goal. So we have done all the intermediate calculations we needed to do. Now I can turn my attention to this particular goal. So let's get to it. No further questions on this? No questions on this? Okay. So while I'm erasing the board, try to cook up a sequence of action so that X of T is equal to that. What sort of UT should I pick? Here is the UT that I'm going to pick. Okay, let's assume for now, I'm going to assume for now that the reachability Gramian is full rank. So assume, I'm going to do the other one. This one is very easy. So that's why I want to make this assumption now that WR0T is invertible, or alternatively range WR0T equals to Rn. So for now, just assume that WR0T is invertible, and I'm going to assume my UT is B transpose A transpose T minus T WR0T inverse XF. This is of course for 0 less than equal to T less than equal to capital T. What is X capital T at this case with this particular? So what is capital X capital T for this? So X naught is equal to 0. I've picked X naught to be equal to 0, right? So the first term is 0. So I have these two terms, but these two terms are actually constant, so I can pull it out of the integral. So I pulled it out of the integral. This one is, so I'm integrating everything that depends on tau with respect to d tau. What is this term? This is exactly WR0T. And so I get xt equals to xf. Okay. So it was, what we have ended up establishing is that I can find a UT if WR0T is invertible, then I can find a UT such that x capital T equals to xf. One thing that I want you to note here is that I have not specified what capital T is. So this seems to work. No matter what capital T greater than 0 you pick, this UT will always work, right? Because that's what the xf we are getting it is. So why do we go through this whole control design process? We can go from any state to any state for any capital T greater than 0. I'll pick capital T to be 0.1 second or 0.2 seconds, and I can go from here to there. Maybe I can't do it in 0.1 second. But technically speaking, this is saying that I can actually do it in 0.1 second. So what's limiting me from actually doing it in 0.1 second?
The system dynamics A?
No, I mean the A dynamics is used here in determining what this control action is. Right? So I can compute this, I can compute everything in this, and I can apply that action and go and hold that knob in like 0.1 second, but I'm taking like, I don't know, 3 seconds or 4 seconds to go from there to there. So what's the problem? Yes.
Your actuator will saturate.
Exactly. Perfect. So the actuators are saturating. So if I pick capital T to be 0.1 second, at least in my case, my actuator is saturating. So UT is going to be extremely large, and that UT can never be applied on an actuator. So one of the reasons why it takes so much time for a robot to do something is because those actuators are constrained, and you have to do a lot more sophisticated control design in order to be able to carry out the mission that the robot is supposed to carry out. Okay, so even though this looks very simple and straightforward, in reality you have actuator constraints, and they will never be able to implement this particular actuation command in capital, if you pick your capital T without understanding what the actuation constraints are. Okay, and different missions will have different actuation constraints, as a result of which you spend a lot more time on control design. But in the unconstrained case, where actuators don't have any constraints, arguably you can apply this control action and you can achieve the objective of reaching a certain state in a finite amount of time. Okay, so always remember, real world actuators have constraints, ideal actuators have no constraints. Okay, so what did I prove? What I proved right now with this exercise is that if WR0T is invertible, then all states are reachable. I can reach any state in the state space if this is invertible. And when is that invertible? If the range of WR, reachability Gramian, is Rn. When is the range of reachability Gramian Rn? When the range of the controllability matrix is Rn. Okay, so the theorem or rather the corollary in the book, which is 5.13. So this is the corollary 5.13. If the range of C is Rn, then all states in Rn are reachable. Then all states in Rn are reachable. Now here is a small story. You know, Wright brothers were the first ones to invent an airplane, or at least that's what we have heard, that's what we have seen in the books. And Wright brothers lived not too far from here. They were less than 1 hour away. They were working in Dayton, Ohio. You know, the important thing that people don't tend to emphasize is it's not that flights were not available before Wright brothers. There were many people who built many flights before Wright brothers, and they all failed to do something. What was that something? Yes.
Actual power control.
Yes. So certainly power was one issue, but the more important issue was the controllability of the flight itself. So the flights were not controllable, and in fact, some of the cases the flights were unstable. We have talked about stability now, so you understand what unstable means. So those flights were unstable, they were uncontrollable, as a result of which they would crash. And Wright brothers actually created the first controllable flight. Okay, and this is exactly what they mean. They created control surfaces, you know, like the things that we hear about. So everybody looks at a bird and says they have wings, and therefore you can, you know, just putting wings on something will create a flying object. But actually that was wrong. There's a lot that happens behind the scenes. So you need vertical tails in the flights, and you need horizontal tails in the flight in order to make the flights controllable. And that's exactly what Wright brothers did. They added a vertical tail and they added horizontal tails in the flights, and that's how they made the flights successful. And now it's a big industry on its own. So what they actually did in mathematical terms, so earlier people had just single B matrix was one dimension, not one dimensional. It had one column, and they added two more columns, which is the horizontal tail and the vertical tail. So they added two more columns. The B became three-dimensional. It had three columns then. It didn't have one column. And then the controllability matrix had full rank. And as a result of which, all states were reachable. As a result of which, they had a controlled flight. As a result of which, their name etched in the history of mankind. Okay. So if you're not able to do something, it means that the range of the controllability matrix is not Rn. Okay, and you need to add new actuators. That's what they did. They added two new actuators on a flight and made it successful. So no other, I mean, I don't remember any bird that has a vertical tail. Okay, they have only horizontal tails, but they are still able to fly. But all flights have to have vertical tails, and only unstable flights have they don't have vertical tails. And some of the fighter planes, because fighter planes are supposed to be somewhat unstable, you will see that they don't have a vertical, they don't have the tail like this, but they will have tails like this, right? So V-shaped tails, and that allows them to do that maneuvering. So this is for all passenger tails, passenger flights, and some fighter jets have this kind of tail structure. Okay, and having this kind of tail makes it very difficult to control, because the controllability matrix is way more difficult. I know we are talking about just the range, but you know, the eigenvalues of the controllability matrix also influences how complicated the control design is going to look like. But we are not going to study that in this class. But if you were to take courses in aerospace engineering, I don't know how many of you are mechanical and aerospace students, but if you take courses in aerospace engineering, they worry a lot about some of these considerations. Any questions so far? all this math was very important, and it allows you to understand how exactly to understand the dynamics of the systems and what states are possible, what states are not possible. So I'm going to keep it here. And now I'm not going to assume that WR0T is invertible. I'm going to make some other assumption. So assume there exists eta1. Okay. Assume x0 is not equal to 0. And there exists eta in Rn such that xf minus e raised to at x naught equals to wr 0t times eta. Okay, so this one is in the range of wr 0t. So in this case, I'm going to take ut to be B transpose exponential A transpose T minus T eta. Then xt equals to xf. So this is my theorem 5.14 in the book. That's what we proved just now. XF reachable from x naught in time t if and only if xf minus e raised to at x naught is in range of wr0t, which is the same as the range of C. I think I'll make another comment, but I'll let you guys write. Okay, so you can reach another state from x naught. Both of them can be non-zero in time t if the difference is actually in the range of the controllability matrix. Okay. So that's the main result. So if your controllability matrix is full rank, then the range of C is Rn, and therefore any state is reachable. If the controllability matrix is rank deficient, which means that it is not full rank, which means that the range is a subspace in Rn, it's not the whole space Rn, then in that case, if you're starting from x naught, then there are only so many states that you can reach from x naught in time capital T. So that characterizes the reachability. So I'm starting here, starting from some position x naught, and I want to reach some particular state xf in finite time, in time capital T. I have a control strategy that allows me to get there, assuming some conditions are met between the initial state and the final state. That's all about reachability. Now I want to talk about controllability. So remember, reachability is going from one state to another. Controllability is going from some state to zero state. So can you get to zero state in finite time? That's what controllability is. So let me tell you about the definition of controllability. I mean, I know we have talked about controllability before, but I want to give you the typical definitions for controllability. Any questions so far on this? The other tidbit of information I wanted to give you, historical information. So anybody remembers James Watt? What did James Watt did? What is he famous for? Yeah. He invented the steam engine, but the fact is he didn't actually create the first steam engine. He just made steam engine controllable. Okay, so prior to him, the steam engines could blow up at any point of time, so it wasn't controlled. And then he created what is known as governors, and that allowed the steam engine to be controlled. And so once again, he created a non-trivial B matrix for the steam engine, and then the steam engine became controllable, and therefore he became the inventor of steam engine. Wonderful. Okay, controllability. By the way, I think some people in controls think that James Watt was the first automatic controls engineer, because that was the first automatic control machine. Like the governor was the first automatic control actuator. I don't know whether that's true or not, but if everybody believes it, I'll believe it. Whatever. It's not going to change my life if I want to dispute this information. Okay. So this is definition 5.18 in the book. X naught controllable if there exist ut such that Okay, so x naught is controllable if I can find a set of, not really a set, but a function of time ut, which is the actions, such that the terminal state is 0 when I start from the initial state x naught. So set of controllable states is denoted by RC, which is the controllable subspace of the system. And the system AB is completely state controllable or globally controllable or simply just controllable. People don't use completely state controllable, they just write controllable if RC equals to Rn. If the set of controllable states is Rn, which means no matter what the configuration of the robot is, it can go to the original configuration within a finite amount of time. Okay, so Roomba is a completely state controllable. So if you run Roomba in the room and whatever it figured out that it has cleaned the room, no matter where it is in the room, it will find its docking station, and it will come and dock and start charging. Okay, so Roomba is a completely state controllable robot, but it's only supposed to move in 2 dimensions. Okay, so it in 2 dimensions, I mean, it is a complicated system, but you can have completely state controllable situations. But if you have a 3D robot or a 6-dimensional robot, or in the case of humanoid, I think they have a 100-dimensional state space. So A would be like a 100 cross 100 matrix, and it has maybe 50 or so actuators. Yeah, I guess how many joints humans have, I don't know how many joints we have, but that would be the dimension of action. Like those are the number of actions available to us. And so I'm kind of curious, are we completely state controllable? Can I move my hand everywhere in the space? I don't know. Maybe not Rn, I cannot reach the space, but yeah, yeah, something to think about. Okay, so what's the important result here? So which is theorem 5.20. Well, before theorem 5.20, let me write down the expression. So my xt equals to 0 is e raised to a t x naught plus 0 to capital T e raised to a t minus tau d u tau d tau. This means e raised to okay. So what I have is e raised to at x naught is in range of the controllability matrix, right? So it follows directly from the definition. So far I have not done anything complicated. So this is what my x of t looks like. I substituted this thing from here, this result, and I got this expression. I pulled this matrix a raised to kb is a constant. So I pull this matrix out of the integral. It doesn't participate in the integral. This is my integral. I'm doing summation of the columns of the controllability matrix times some vector. That means that e raised to at x naught. So I know that I have a negative sign here, but range is sort of sign invariant. So e raised to at x naught must be in the range of C. But it's nice to know if x naught is in the range of C. But if I have e raised to at x naught in the range of C, does that mean x naught is in the range of C? Is that true? If e raised to at x naught is in the range of C, does that mean x naught is in the range of C? Turns out that that's the case because of the following lemma, lemma 5.19. And now I can erase this side. No. And this would further imply that e raised to at x in the range of C. Okay, so this statement is proved in lemma 5.19. It's actually extremely simple and uses Cayley-Hamilton theorem. This one is proved in theorem 5.20, which I'm going to talk about next. But that gives you an idea that if this one has to be in the range of C, then x naught should also be in the range of C. So theorem 5.20, which is the most important result from controllability and reachability perspective. X is reachable if and only if X is controllable. R equals to RC. So the reachable subspace is the same as the controllable subspace. And the third one is global reachability if and only if global controllability. So in a linear system, it's not necessarily true in a nonlinear system, but in a linear system, if you can reach a specific spot, then you can also control that specific, you can get to zero from that particular spot. Okay, so controllability matrix, this matrix, the rank of this matrix tells you what states are reachable, what states are controllable, and whether or not you have global reachability and global controllability. Because it turns out that in the linear system context, controllability and reachability are very similar concepts. It may not be the case in nonlinear system, but definitely it's the case in linear system. I'm not so sure about the nonlinear systems area because I don't study it. I've not studied it in the past, so I don't know about that part. But at least as far as the linear system is concerned, ideally you want the controllability matrix to be full rank. If your controllability matrix has lower rank, then you have a problem in the system. There are certain states that are not reachable, and there are certain states that are not controllable, and you should be okay with that design, that particular system is not reachable or not controllable. So for instance, so some of the toys that my kids have, they can only go in forward direction, they can't go in the backward direction, right? So some states are not reachable there. Anyone knows why we are able to drive the car? One quote that I read, which sort of has stuck with me for a long time, I don't remember where I read it, that the reason why people drive the car is because they can stop the car. If you can't stop the car, you will never drive the car. Okay, so I know it's a very profound statement, but for some reason I never thought about it until I actually read that statement. Uh, so so yeah, I mean, in many cases, whenever you are in this robotics business or any business that requires you to design a control system, you have to be very, very confident about the reachable sets, controllable sets. And when you are, for instance, when you are driving autonomous car on the road, and if an accident is happening in front of you and you want your vehicle to stop, that's exactly a controllability problem. And you want to be able to predict the accident way in advance so that you can control the system to reach a stop before the accident happens. Okay. And one situation where you lose controllability is when you have ice on the road, sleet on the road, right? So, we've had a rough winter this year. And there were instances, I think, in northern Michigan, where there was 100 cars collided on the highway because there was a complete loss of controllability because the road was full of just sleet. Uh, so so then there is a loss of controllability, and therefore you don't drive your car. So always remember, the reason we drive the car is because it is controllable, because you can get it to a stop whenever you want it to. If that wasn't the case, you wouldn't drive your vehicle. So that's all I have for today. I think the proof of 5.19 and 5.20 is very similar to whatever stuff we have done in the class today. So you should be able to go through the proof on your own in the book, from the book. In the next class, I'm going to talk about the counterpart of controllability and reachability, which is observability and constructibility. So if you have observation as well, so right now we didn't care about the observation equation, we just care about the state equation. Next class, we'll talk about the observation equation, and we'll talk about when is a system observable and when is a system constructible. And then we'll study conditions under which you can have observability and constructibility. So thank you so much, and I'll see you on Thursday. Oh, important announcement, next week is break. So there is no office hours and there is no class on Tuesdays and Thursdays. Enjoy your break. Okay.